The other wheels, a bicycle frame has a mass of 8 kilograms, 16 pounds, okay. Each, maybe 20. Each of the wheels can be roughly modeled as a uniform solid disc with a mass of 0.82 kilograms and a radius of that. Okay. Seems kind of small. That's okay. Find the kinetic energy of the whole bicycle when it's moving at 3 meters per second. Okay, so we're going to draw a picture of our bicycle. We're going to assume 2 wheels, i.e. bi. And that's a terrible picture of a bicycle. That's even worse. Hoop. This is tragically bad. All right, so we're going to find energy kinetic total, which is going to be energy kinetic, I'm going to call F for frame, plus 2 times energy kinetic wheel, W for wheel. And so energy kinetic frame is going to be equal to, it's just moving linear, no rotational. And so it's going to be 1/2 mv squared. This will be mass frame. So it would be 1/2, I'm just going to leave it as 1/2. Now I'll come up with an answer. Mass is 8. Velocity is 3 squared. That gives us a value of 0.5 times 8 times 3 squared. I could have totally done that in my head. 36. Now we're going to do energy kinetic of wheels. So energy kinetic of the wheel is going to be, I'm going to call this energy kinetic linear plus energy kinetic rotational. And we could have done the same setup with the bike frame, and then just been like, well, the rotational energy is 0. So it's not like this is a unique formula that I'm applying to the wheels. I applied it to the frame as well. It's just that one part was 0, so we ignored it, and we kind of skipped over some nuance there without commentary. This becomes 1/2 mv squared plus 1/2 I omega squared. And then I'm going to say, well, I of the wheel is 1/2 mr squared. This is the radius of the wheel. I'm going to look that up real quick just to make sure I'm not too far off of reality. So solid disk, which I think is what we approximate the wheels as, 1/2 mr squared. So I'm not saying we're right, I'm just saying we're not obviously wrong. So the relationship between linear and angular, x equals r theta, v equals r omega, a equals r alpha. The one we care about is right there because we have omega, which is angular speed. Omega equals v over r, therefore omega squared is v squared over r squared. And so then we're going to rewrite this as 1/2 mv squared plus 1/2 times 1/2 mr squared times v squared over r squared. Lots of math, but not, the concept's not too bad. The r squareds cancel, and we're left with 1/2 mv squared plus 1/4, 1/2 times 1/4 mv squared. This gives us 3/4 mv squared, and therefore 2 times energy kinetic wheel, so 2 energy kinetic wheel because 2 wheels, equals 3/4. Now 2 times 3/4 times mass wheel times velocity squared. Yeah, I'm good with that. And so the 2 and the 3 becomes 6. That becomes 3/2. 3/2, mass wheel, velocity squared, energy, which I can totally just get an answer to right now. This becomes 3/2. Mass of the wheel is 0.82, 0.82. And the velocity of the wheel is 3. I guess, yep, 3. And that's the velocity at the center of the wheel. 3 squared. And then put calculator. We get an answer of 1.5 times 0.82 times 3 squared. 11.07. 11.07. And this is joules. Joules. So going back to our original equation up here, energy kinetic total is therefore 36 plus 11.07. I'm just going to take my 1.5 times 0.82. Is it 0.82? 0.82, yep. And you notice how the radius of the wheel doesn't actually matter in this case. And that's because there's a relationship between the linear motion and the rotation of the wheel. 47.07 joules. That's the total kinetic energy of the bike, including the frame and the 2 wheels. All right, it's basically a completely different question. All right, we got this. For the invention of the wheel, turning on an axle, ancient people used moved heavy loads by placing rollers under them. Modern people use rollers too. Any hardware store will sell you a roller bearing using a Lazy Susan. A stone block of mass 800 kilograms moves forward at 0.3 meters per second, supported by 2 uniform solid cylindrical tree trunks, mass of 82 kilograms, and a radius of 0.343 meters. No slipping occurs between the block and the rollers. Find the kinetic energy of the moving objects. Okay, so there is an important nuance in this that we're going to have to not run afoul of. So I'm going to move this over here and maybe a little bit further. All right, so like all good physics problems, we're going to start by drawing a picture. And so we're going to draw a slab like so. Then we're going to draw some tree trunks. 1, 4 divided by 2. There's so 2 tree trunks. Yes. So the key concept here is with a bicycle, the bicycle is attached to the wheels at the center, where the slab is attached more or less to the tree trunks at the top. And so the speed, the stone block is going to be moving forward at 0.3 meters per second. Well, if you have a wheel that's rolling, and this is one of those things where you don't, it intuitively does not make sense, but it's true. When a wheel is rolling and not slipping, the bottom is not moving. So V equals 0, velocity equals 0, and it rolls. It's rolling without slipping. The center is going to be moving at velocity equals V, and the top is going to be moving at a velocity V equals 2V. And so the idea here is this block right here is moving at 3 meters per second, which means that point at the top is moving at 0.3 meters per second. Right here, velocity is going to be 0.3 over 2, which is going to be 0.15 meters per second. And that's going to be the big key difference between problem A and problem B. If you ever see videos of people rolling things on logs, which you might at some point in life, there's probably videos, YouTube. The rolling logs are going to basically fall off the back, and you have to basically grab the log and put it in front. The reason that is because the logs are rolling at half the speed of the slab on top. And that's what we're going to have to take into account here. Okay, so now we want to find the total kinetic energy of the objects. At this point, we're going to do the exact same concept we did before. Energy kinetic total is energy kinetic slab plus 2 times energy kinetic of the rollers. Energy kinetic slab is 1/2 m slab v squared, which is going to be 1/2 times 800, quite the beefy slab, times 0.3 squared. And so then that gives us, back to our calculator, 0.5 times 800 times 0.3 squared. That gives 36 again? Weird. Did not see that coming. 36. Energy kinetic roller is now interesting. Maybe I should have foreseen that. I did not. Energy kinetic roller is going to be 1/2 mv squared plus 1/2 I. Need to get a better way of making i's. I omega squared. I is, I think it's going to be the same, 1/2 mr squared. Yep. So solid cylinder radius r along the z-axis right there, 1/2 mr squared. So it's going to be the same as a disk. And so this is going to be 1/2 mr squared. I'm going to know this is mass of the roller. I'm not going to differentiate here, but we both know. Omega, which is the angular speed, is v over r. Check that over here, just make sure that's something similar I did over here. Omega is equal to r, yep. Therefore, omega squared equals v squared over r squared. I know I should use only capital, only lowercase. I should be more consistent. I am not. So then we have 1/2 mv squared plus 1/2 times 1/2. Yep, this is energy kinetic of one roller. 1/2 times 1/2 mr squared times v squared over r squared. R squareds cancel, and we are left with 1/2 plus 1/2, which gives us 3/4 mv squared. 1/2 plus 1/4 is 3/4. Therefore, 2 energy kinetic rollers is going to be 3/2 mv squared. Yes, that's the same thing we got over here. 3/2 mv squared. Yep. Or in this case, though, v is 0.15 meters per second, not 0.3 meters per second. And that's going to be the key difference here. So going back to our values, 1.5 times mass of said roller. Each has a mass of 82 kilograms. 82 times, probably going to get the same answer. 1.5 times 82 times 0.15 squared. 1.5 times 82, yep, 2.7675. Energy kinetic total is therefore 2.765 plus the mass of the slab, which is 36 plus 36. This gives us a value of about 38.8 joules, which is less than the previous one. And I think the main difference is because the rollers are moving slower than the wheels. And that's because of how the rollers are connected to the slab. The slab is sitting on top of the rollers, while the bicycle wheels are connected at the axis, at the center of rotation. And that's the big difference, the key takeaway from this one. All right. So, summary, recap. The big idea here was we want to find the energy kinetic of a system with both rotating and non-rotating parts. When we do that, we would just take the kinetic energy of each individual part, add them all together, and specifically, when we look at the kinetic energy of an object, it's just energy due to motion, and I broke that down into energy linear plus energy rotational. And you can do that with pretty much everything. It's just that most problems you're given, it's either moving linearly or it's rotating. So, and in the case when you have both, you just put them both in the equation. So the idea is that energy is measured in joules. It's a scalar. You have two piles of energy, you put them together, you get a bigger pile of energy. Nothing more subtle than that. Hope that helped. See you in the next problem.